The Cloud Router Availability Challenge. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Today, we're looking at a real-world scenario that tests your understanding of Google Cloud networking high availability. This question comes from a certification exam or interview scenario, and it's exactly the kind of challenge you'll face when designing resilient hybrid cloud architectures. Let me read through the scenario. Your company has a dedicated interconnect as the hybrid connectivity between its VPC, with default dynamic routing, and the on-premises network. A single cloud router is used to dynamically exchange routes between both networks. The GCP VPC has one subnet with resources deployed. You have been asked to improve the availability of the cloud router in case of a region-wide failure. Now, here's what makes this interesting. We have 4 different approaches to solve this problem, each with its own trade-offs. Some protect against regional failures, others against router-level failures, and one takes a completely different approach using static routes. As we go through each option, I'll explain not just what to do, but why each approach works and when you would choose one over another. Let me show you exactly what this current architecture looks like and why it's vulnerable. As you can see in the diagram, we have a classic hybrid cloud setup using Google Cloud's dedicated interconnect. This provides a physical connection between your on-premises data center and Google's network. Think of it as your private highway to the cloud. At the heart of this connectivity sits a single cloud router. This isn't just any router. It's running BGP, the Border Gateway Protocol, to dynamically exchange routes between your VPC and on-premises network. When someone in your data center needs to reach a cloud resource, or vice versa, the cloud router ensures both networks know how to find each other. Now here's the critical vulnerability. Everything depends on this single cloud router in one region. If that region experiences an outage, and yes, this does happen in the real world, you lose all connectivity between your cloud resources and on-premises infrastructure. Imagine your critical database is in the cloud but your applications are on-premises. A regional failure means a complete application outage. Notice the default dynamic routing mode mentioned in the scenario. This is regional routing, meaning routes learned by the cloud router are only programmed into the VPC within that specific region. This detail becomes crucial when we look at our solution options. Option 1. Different region with global routing. Let's dive into our first option, which provides the highest level of availability. This approach involves creating another cloud router in a completely different region and switching the VPC to global dynamic routing mode. This is the most comprehensive solution to the regional failure problem. Here's how global routing changes everything. When you enable global dynamic routing mode, routes learned by any cloud router in your VPC are automatically propagated to all regions where you have resources. Think of it as upgrading from a regional phone book to a global directory. Suddenly everyone knows how to reach everyone else, regardless of location. In this setup, you'd have Cloud Router 1 in, say, US Central 1, and Cloud Router 2 in US East 1. Both routers establish BGP sessions with your on-premises network through their respective interconnect attachments. During normal operations, both routers share the routing load. But here's the magic. If US Central 1 goes down completely, the cloud router in US East 1 continues to advertise routes for your entire VPC, including resources in the failed region. The catch? You need interconnect presence in multiple regions. This means either ordering a second dedicated interconnect in another region or using partner interconnect to extend your reach. This adds cost and complexity, but for mission-critical workloads, it's often worth the investment. I've seen this save companies during actual regional outages. The failover is seamless because the routes are already propagated globally. Implementing option 1 with G-Cloud. Now let's walk through the actual implementation commands for option 1. I'll explain each parameter and why it matters for your high availability setup. First, we create the cloud router in a different region. Notice the region equals US East 1 parameter. This is crucial. You must choose a region different from your primary router. The ASN, or Autonomous System Number, comes from the private ASN range. Each cloud router needs a unique ASN within your project. Think of the ASN as the router's identity in BGP conversations. Next comes the interface configuration. The interconnect attachment parameter points to your VLAN attachment in the secondary region. This is where many people get stuck. You need to have already created an interconnect attachment in this region. If you're using dedicated interconnect, this means having physical connectivity there. Partner interconnect can be a more flexible option here. The BGP peer configuration is where you tell your cloud router how to talk to your on-premises router. The peer ASN must match what's configured on your on-premises side. Getting this wrong is a common mistake that prevents BGP sessions from establishing. Finally, the game changer command. Updating the VPC to global routing mode. This single command transforms how routing works across your entire VPC. After running this, routes from both regions are shared globally. I always recommend checking the routing table after this change to confirm routes are propagating as expected. Option 2. Same region with global routing, takes a different approach. We keep both cloud routers in the same region but still enable global dynamic routing mode. At first glance, you might wonder, if both routers are in the same region, how does this improve availability against regional failures? That's a great question, and the answer reveals an important nuance in high availability design. This option protects against cloud router level failures rather than regional failures. Think about all the things that can go wrong with a single router: hardware failures, software bugs, misconfiguration during maintenance, or even hitting BGP session limits. With two routers in the same region, you're protected against all of these scenarios. Here's a real-world example. I once worked with a financial services company that experienced a cloud router failure due to a memory leak in the BGP daemon. It wasn't a regional issue, just that one router stopped processing routes correctly. If they had implemented option 2, the second router would have maintained connectivity without any manual intervention. The beauty of this approach is its simplicity. You can use your existing dedicated interconnect in the same region. Both cloud routers connect to the same interconnect but use different VLAN attachments. Most dedicated interconnects come with two VLAN attachments by default, so you're just making better use of what you already have. The global routing mode still provides benefits here. If you later expand to multiple regions, the routes will automatically propagate everywhere. Let's implement option 2. The commands are similar to option 1, but with a crucial difference: we're staying in the same region. This makes the implementation much more straightforward. When creating the second cloud router, notice that the region parameter, US Central 1, matches our primary router's region. The ASN 64522 is different from our first router. It's important to remember that BGP requires unique ASNs for different routers. I typically use sequential ASNs for easier management, like 64520, 64521, and 64522, making it clear which routers belong to the same project. The interface configuration is where this setup shines. We're using my attachment VLAN 2, which is typically the second VLAN attachment on your dedicated interconnect. Most dedicated interconnects come with two 10 gigabits per second VLAN attachments, and many organizations only use one, leaving the second attachment idle. This option puts that idle capacity to work for redundancy. For the BGP peer, we're using the same peer ASN, 64521, as the first router because we're still talking to the same on-premises device. This is different from option 3, where we would have different peer ASNs for different devices. The on-premises router will see two BGP sessions from Google's side and can load balance between them. Don't forget to enable global routing mode. Even though both routers are in the same region now, This prepares you for future multi-region expansion and ensures consistent routing behavior across your VPC. Option 3 introduces redundancy from a completely different angle. Instead of just adding another cloud router, we're creating a fully redundant path by connecting to a second on-premises device. This is often the most practical solution for enterprises with existing network redundancy in their data centers. Let me paint a picture of when this shines. Imagine your data center has two core routers for redundancy. Let's call them Router A and Router B. Currently, only Router A connects to Google Cloud through the cloud router. If Router A fails, you lose cloud connectivity even though Router B is sitting there, fully functional. Option 3 fixes this by creating separate cloud router to on-premises router pairs. This creates true end-to-end redundancy. Cloud Router 1 talks exclusively to your on-premises Router A, while Cloud Router 2 talks to Router B. Each pair operates independently with its own BGP session. If any component fails, whether it's a cloud router or an on-premises router, the other pair continues operating normally. From my experience, this option is particularly popular with enterprises that follow traditional network design patterns with primary/backup router configurations. Your network team will appreciate this because it mirrors their existing redundancy model. The path selection can be controlled using standard BGP attributes. For example, Router A could be preferred using local preference or shorter AS paths, with Router B as the automatic backup. Implementing Option 3 requires close coordination with your on-premises network team, but the cloud-side configuration is straightforward. Let me walk you through the commands and the critical details that make this work. First, we create a second cloud router with ASN 64523. Each cloud router needs its own ASN, just like in Option 2. The region stays the same, US Central 1, since we're not trying to protect against regional failures here. Instead, we're building device-level redundancy. The interface configuration uses the second VLAN attachment, just like in Option 2. But here's where it gets interesting. Look at the BGP peer configuration. The peer ASN is 64525, which is different from our first router's peer ASN of 64521. This is the key difference that makes Option 3 unique. This new ASN belongs to your second on-premises device. Your on-premises team needs to configure their second router, Router B, with ASN 64525 and establish a BGP session with your cloud router 2. They'll also need to ensure both on-premises routers can forward traffic to each other internally. This is usually already in place in enterprise networks, but it's worth confirming. After implementation, I always run the G-Cloud Compute Routers Get Status command to verify both BGP sessions are up. You should see two active BGP sessions, each learning the same on-premises routes but from different sources. This redundancy means that even if one entire router pair fails, traffic continues flowing through the other pair without interruption. Option 4. Static Routes Backup. Option 4 is fundamentally different from the others. Instead of adding another cloud router, we're configuring static routes as a backup. This is the simplest option, but as with many simple solutions, it comes with significant trade-offs that you need to understand. Here's the elegant simplicity of how it works. In Google Cloud, routes have priorities, with lower numbers meaning higher priority. BGP learned routes typically have a priority of 100. So we create static routes with a priority of 200. During normal operations, the dynamic BGP routes win because 100 beats 200. But if your cloud router fails and those BGP routes disappear, the static routes automatically take over. No manual intervention is required. Now for the reality check. Static routes are, well, static. They don't adapt to network changes. If your on-premises team adds a new subnet next month, your static routes won't know about it. If they change IP ranges or redesign the network topology, you'll need to manually update every static route. I've seen this become a maintenance nightmare in dynamic environments. So when does Option 4 make sense? It's perfect for stable networks that rarely change, or as a temporary solution while you implement one of the other options. I've also seen it used successfully in lab environments or for specific, critical subnets that never change. Just remember, this protects against cloud router failures, not regional outages, since the static routes still rely on the interconnect in the same region. Implementing option 4. Let's implement option 4 with static routes. While this is the simplest option technically, it requires the most careful planning upfront because you need to know exactly which on-premises networks to route to. In our first command, we're creating a static route for the 10.0.0.0/8 network. This is one of the RFC 1918 private address ranges that many organizations use internally. The key parameter here is priority, set to 200. This must be higher than your BGP route priority. Remember, a higher number means a lower priority. BGP routes default to 100. So 200 ensures our static route only activates when BGP routes disappear. The next hop interconnect attachment parameter is crucial. It points directly to your VLAN attachment, bypassing the cloud router entirely. This is why the route survives cloud router failures. The traffic still flows through the same interconnect, just without dynamic routing. You'll need to create a static route for each on-premises network range. In the example, I'm showing 10.0.0.0/8 and 172.16.0.0/12, but your organization might have dozens of ranges. This is where the maintenance burden becomes apparent. Pro tip: I always recommend documenting these routes extensively, including why each range exists and who owns it on premises. After creating static routes, run G-Cloud Compute Routes List with a filter for your VPC. You'll see both types of routes. The BGP routes with a priority of 100 actively carrying traffic, and your static routes with a priority of 200 standing by as backups. It's like having an emergency generator, hopefully never needed, but ready to kick in when the power fails. Comparing the options. Now let's put all 4 options side by side and analyze them comprehensively. This comparison will help you make the right choice for your specific situation. Looking at protection levels, option 1 is the clear winner for maximum availability. It's the only option that protects against complete regional failures. I've seen this save organizations during major regional outages. While others scrambled to restore connectivity, option 1 implementers continued operating normally. Options 2 and 3 provide excellent router-level redundancy within a region, while option 4 offers basic failover capability. Cost-wise, option 1 is the most expensive because you need connectivity in multiple regions. This might mean a second dedicated interconnect for over $1,700 per month or partner interconnect fees. Options 2 and 3 are much more economical. They typically just use your second VLAN attachment, which you're probably already paying for. Option 4 has zero additional infrastructure cost, making it attractive for budget-conscious deployments. Complexity varies significantly. Option 1 requires the most planning and coordination, especially if you need to establish connectivity in a new region. Option 4 is simple to implement but becomes complex to maintain over time as your network evolves. Options 2 and 3 strike a nice balance, moderate implementation complexity with straightforward ongoing maintenance. For best use cases, choose option 1 for mission-critical workloads where downtime costs far exceed infrastructure costs. Options 2 or 3 work well for most production environments. Option 4 should be reserved for stable, simple networks or as a temporary measure while planning a better solution. Best practices and recommendations. After implementing Cloud Router high availability for dozens of organizations, I've learned what works and what doesn't. Let me share the best practices that will save you time and prevent outages. First, always start by documenting your current routing setup. Run the G-Cloud Compute Routers Get Status command and save the output. Document which routes are critical versus nice to have. This baseline is invaluable when things go wrong at 3 a.m. and you need to quickly understand what's changed. For most organizations, I recommend starting with option 2 or 3, then evolving to option 1 as your cloud footprint grows. Option 2 is perfect if you have simple on-premises connectivity with one edge router. Option 3 shines when you already have redundant on-premises routers. It's the path of least resistance that leverages your existing investments. Testing failover is crucial but often skipped. Schedule maintenance windows to actually fail your primary cloud router and verify the backup takes over correctly. Watch for route convergence time. It typically takes 30 to 60 seconds for BGP to detect failure and reconverge. Some applications might experience brief disruptions during this time. Don't forget monitoring. Set up alerts for BGP session state changes, route count anomalies, and interconnect attachment status. The best high availability setup is worthless if you don't know when half of it has failed. Finally, remember that high availability is a journey, not a destination. Start with what makes sense today, but plan for tomorrow. Maybe option 2 works now, but as you expand globally, option 1 becomes necessary. Thank you for your attendance. Please consider subscribing to the channel.